Okay, so when we last left off, we were discussing resonance effects on observed hybridization of different atoms participating in resonance. And now we're going to look at the effect or the contributions of different resonance structures into the overall bond order. Now, the actual bond order of a molecule is a weighted average of the bond order found in each resonance structure. So for example, if you're trying to calculate the average bond order for a given bond, first and foremost, you need to draw all the major contributing resonance structures, determine the bond order of the given bond in each structure, and then you're going to take the average of each of the bond orders observed for a given bond in each of the contributing resonance structures. So for example, if we're looking at NO2 minus, for example, so NO2 minus, we have 18 electrons to work with. Two, 4, 6, 8, 10, 12, 14, 16, 18. We then replace one of our lone pairs with a double bond. So now we have a complete initial structure for NO2 minus or nitrite. Now what we have to do is we have to draw a series of resonance structures. And in this case, we'll kick our lone pair down, our double bond gets kicked up and converted into a non-bonding lone pair. And that in turn gives us the following resonance structure. So these are our two major resonance structures. So now what we have to do is we have to look at the average bond order for each of these two structures. So I'm going to label them bond 1 and bond 2. So in bond 1, in this top structure, what is the bond order? How many bonds are present between nitrogen and oxygen? How many bonds are present? 2. So we have a bond order of 2. Okay. In the second structure, what is the bond order for bond 1? 1. So we have 2 plus 1. And then we divide by our total number of resonance structures, which would be 2. And that gives us a bond order of 1.5. We can repeat the same process for bond number 2, where our bond order is equal to the bond order in our first resonance structure plus the bond order in our second resonance structure divided by the total number of resonance structures. And that in turn gives us an average observed bond order of around 1.5. What this is telling us is that we don't quite have a single or a double bond. Instead, we have a bond that is slightly stronger than a single bond, but weaker than a double bond. Does this idea make sense to everyone? Any questions on this idea? So let's take a moment and let's look at carbonate. Let's look at carbonate. So our first, so it's CO3 2 minus. So our first structure for carbonate would look something like this. Now we can push our electrons and generate a few resonance structures. So let's generate two resonance structures using our arrow pushing method. We kick our lone pair down, our double bond breaks accordingly. Continuing this process, we can draw one more major contributing resonance structure. And that in turn gives us the following set of resonance structures. Now, my question to all of you is, if we study and we really focus on the bond order for this top bond here, that I'm going to label as 1. Let's do a calculation for the bond order for bond 1. So in our first resonance structure, what is our observed bond order? In our first resonance structure, what is our observed bond order? 2. Okay, what about in the second structure? 1. Finally, in our third resonance structure, what is the bond order? 1. Then we divide by the total number of resonance structures, which is 1, 2, 3. And that gives us a value of 4/3, or a 1 1/3 bond order. So even though both of these bond orders in these two different compounds are fractional bond orders, as we can clearly see, we would expect this nitrogen-oxygen bond to be stronger because 1.5 is greater than 1 1/3. So by drawing out and looking at the bond order in each of the contributing resonance structures, you can estimate and you can compare bond strengths accounting for resonance contributions. Does that make sense to everyone? Any questions on this example? So, as we can see, we have two fractional bond orders, right? But the nitrogen-oxygen bond order is 1.5. So it's a little bit stronger than our carbon-oxygen bond if we just consider the bond order number. So by calculating the average bond order, considering and taking into account resonance effects, we can compare the relative strength of different bonds while accounting for the effect of resonance contributions on our observed bond strength. Any other questions on this example? If not, let's keep going now. And I'd like you to work on this example for about 2 minutes, and I'd like you to tell me which carbon-carbon bond is the strongest in the following structure. There are 6 carbon-carbon bonds. And I'd like you to tell me what is the carbon-carbon bond order. So let's take about 2 minutes on this example, and don't be shy to share your responses in the chat. And as we already see in the chat, someone's getting very close to the key point in this question. So let's keep working on this example. Don't be shy to share your responses in the chat, and I'd like to see some calculated number values for the bond order. And we'll discuss in about 1.5 minutes. And don't be shy to share your response, even if it necessarily disagrees with your classmates. I just want to see a nice pool of responses before we discuss. If not, we'll talk about this example in about another minute. Okay, so there seems to be consensus for this example. So first, let's draw out the resonance structure. So for cyclic, in this case, aromatic systems, we can move each of our double bonds one space over, and that would generate the following resonance structure. So if we focus in on any single one of our carbon-carbon bonds, we notice that in one resonance structure, there's a double bond. In the other resonance structure, there's a single bond. So if we're calculating the bond order, all we have to do is add up the bond order observed in each of our major contributing resonance structures. So we have 2 plus 1 over 2, and that gives us a bond order of 1.5. So the carbon-carbon bonds in benzene are not quite double bonds, but they're certainly stronger than your typical single bond. There are a few other factors at play that make the bonds found in benzene a little bit stronger than usual, but we'll talk about those a little bit later on in this class. Does this make sense to everyone? Any questions on this idea? Any questions before we move on to the next example? If not, let's keep going. Now, I'd also like you to try and answer the question. Same structures. I'd like you to tell me which carbon-hydrogen bond is the strongest. So is there any difference between the carbon-hydrogen bond strength for each of the carbon-hydrogen bonds in benzene? So let's think about this for about a minute to a minute and a half, and don't be shy to share your responses in the chat. Which carbon-hydrogen bond is the strongest, or are they all equally strong? So if we're thinking about benzene and looking at each of our carbon-hydrogen bonds, are each of these carbon-hydrogen bonds equally strong? So if we look at both of our contributing structures, so if we look at both of our contributing structures, we notice that in each of our structures, the hybridization for each of our carbon atoms is sp2. So there's no difference in the resonance structures comparing the hybridization. Also, looking at the hybridization of each of our carbon atoms in benzene, we have the same observed hybridization, and we have the same observed carbon-hydrogen bond order. So we would conclude that all of our carbon-hydrogen bonds are equally strong in this structure, because there's no discernible difference between the carbon used for bonding and the bond order. But it's really important to identify the hybridization of your bonding atoms because that directly impacts bond strength. Any questions on these examples? Any questions that I can address? If not, let's keep going. So I have a pair of examples now. I'll do the first one, you'll do the second one. So we're going to be comparing two structures. We're going to identify which structure has the strongest carbon-oxygen bond. We're going to indicate the hybridization of each atom in the structure. And we're going to indicate which structure has the shortest carbon-carbon bond. Okay. So first and foremost, we need to draw each of our contributing resonance structures. Okay, so for this first structure, we can very easily delocalize our electron density into our ketone functionality. That in turn would give us a resonance structure that would look something like this. Oops. Let me change the pen color so it's a little bit easier to see. Now, of course, this structure is a minor contributor, but nonetheless, it plays a pretty important role in terms of helping us understand how these resonance effects can begin to impact our bond length and bond strength. So we're just going through and we're drawing as many of our possible resonance structures as we can.
Major and minor structures differ in the fact that minor structures typically give off more formal charges to the atoms, right?
Yes, yes. So these structures are relatively minor in terms of their contribution, but they're not completely negligible because they are still fulfilling the octet rule, and the formal charge placement is not completely illogical. We have negative formal charges on electronegative atoms. We have positive formal charges on, generally speaking, less electronegative atoms. Though in this case, the positive formal charge placement is part of why this structure is not particularly favored. Very good point. Very good comment as well. So we're going to continue on with drawing our potential resonance structures. And the main thing to consider in these sorts of problems is not an absolute calculation of the bond order. Instead, what we're looking for is a relative calculation that helps us get a sense of the relative distribution of electron density in your molecule, okay? So we draw out a few resonance structures for our first molecule on the left. Let's look at our molecule on the right for a moment. And let's consider what's going on in terms of resonance structures. So this structure has far less possible resonance structures because there are far less atoms conjugated to our pi system. Okay, so we have our first resonance structure, and we can continue moving our electron density to generate our second resonance structure. Okay, now with this information established, we can then start to draw some conclusions. About our overall bond order, and we can begin to answer each of these questions. So for the first question that we have is the carbon-oxygen bond order, okay? So which of these two structures has the strongest carbon-oxygen bond? Well, the way to go about answering that question is to look at as many of our contributing resonance structures as possible and to count up the total bond order and average it out over each of our resonance structures. So let's do just that. So if we're studying this carbon-oxygen bond right here, let's look at the bond order for the carbon-oxygen bond. So in this first structure, what is the carbon-oxygen bond order? What is the carbon-oxygen bond order? In this first structure on the left, this one right here. 2, okay, so we have 2. Okay, what's the bond order in this next structure here? 1, okay. What about this next structure here? 1. And finally, what about this bottom structure? 2, okay. We're then going to divide by the total number of possible resonance structures, and that gives us a bond order of 6/4, which is 3/2. This is our bond order for our carbon-oxygen bond from this first structure. Let's look at our second structure now. Let's calculate our average carbon-oxygen bond order. So in this case, we have 2 plus 2 plus 1 over 3, and we have an average bond order of 5/3. So, which bond is stronger? Which bond order is greater? The top structure or the bottom structure? The bottom structure. So we have a stronger carbon-oxygen bond. Another way to think about this, if you don't want to manually calculate each of your bond orders, the more atoms that you have participating in resonance, the more atoms that you're distributing your electron density over. So in this case, we have 6 atoms compared to 5 atoms. The more atoms that you're distributing and delocalizing your electron density across, in general, the weaker your average bond order is going to be, assuming the same amount of electrons distributed. So because we have this additional oxygen atom in the top structure, we can in turn delocalize our electron density found in our carbon-oxygen bond over multiple additional atoms. So it's over 1 additional atom. And as a result, the amount of electron density on average in this carbon-oxygen bond is less than in this bottom structure. Does that make sense to everyone? So if you have the same amount of electron density distributed over more atoms, you're going to have weaker bonds because there's less electron density in that individual bond. Does this idea make sense to everyone? Does this first idea make sense to everyone? Okay, so now let's look at our second case. Let's look at our second case. And let's look at our carbon-carbon bond order. So the shortest carbon-carbon bond has the greatest bond order. So let's just look at our original bond here. So we're going to focus in on this bond, okay? And just as a first pass, before we actually put any numbers to it, which carbon-carbon bond would we expect to be shorter? Would we expect to have the larger bond order? The structure on top or the structure on the bottom? We would expect, just intuitively, that the structure on the bottom would likely have the larger bond order value. So let's see how this pans out. So we have a bond order of 2 in our first structure, a bond order of 1 in our second structure, a bond order of 1 in our third structure, and a bond order of 1 in our fourth structure. If we divide by our total number of resonance structures, that gives us a bond order of 5/4. Okay, let's look at this next bottom example. So we have a bond order of 2 in our first structure, a bond order of 1 in our second structure, and a bond order of 1 in our third structure. And we divide this out and we get 4/3. So as we can see, we have a shorter and stronger carbon-carbon bond in our bottom example, because the average bond order is greater. You can consider both. So this carbon-carbon bond order, it's the same for each of these bonds. And yes, it would be important to consider both. The reason why I'm focusing on just one of our carbon-carbon bonds is if we wanted to analyze this second set of carbon-carbon bonds, note that this second carbon-carbon bond is primarily found in your minor structures. So even though we have these structures that have a lot of double bond character, the contribution from these structures on the right are relatively minor compared to the structure on the left where it's neutral. So this counting method is not designed to give you exact bond orders. It's designed to help you approximate the bond order and compare the relative strength and length of bonds in two different structures. So the exact bond order is probably a little bit greater than 5/4. This neutral structure has a slightly greater contribution. What I'm trying to get you to visualize, what I'm trying to get you to start to understand is the more atoms you're distributing the same amount of electron density over, the weaker your bonds are going to be. Does that make sense? Does that initial idea make sense to everyone? So you draw out all of your resonance structures. We note the neutral structure is typically going to be major. It's typically going to be a greater contributor. And with that weighted contribution in mind, we pick a single bond and we calculate the bond order across all of our resonance structures in each of our two unique molecules. We compare the bond order, and the species with the greater value for our bond order will be a stronger and shorter bond. Does that make sense? Now that we've done all of this work identifying all of our different resonance structures, we can now identify hybridization. So anytime we have an atom that's participating in resonance, I'm going to put a little star next to it. Anytime we have an atom that's participating in resonance, what must the hybridization be for this oxygen if it's participating in resonance? If it has its lone pair in a p orbital connected to our pi system, what must the hybridization be at minimum? sp2, exactly right. So each of these oxygens are sp2 because the oxygens have a lone pair in our p orbital. That's how it's able to participate in resonance. Does that make sense to everyone? So this is where organic differs from general chemistry in that resonance effects impact the observed hybridization and the observed geometry for your molecules. So these oxygens are actually flat rather than bent. Pretty interesting, actually. Okay, what about this carbon that I'm pointing to? What's the hybridization of this carbon? That's a bit of a freebie. What's the hybridization of the carbon? sp2, yep. These are sp2 carbons. And this oxygen, I'm gonna put in quotes sp2 because for oxygens just bonded to one atom, it's ambiguous whether or not it's hybridized. I would give you full credit if you label it sp2. That's a perfectly reasonable way of conveying the geometry and the fact that this oxygen has a p orbital that is using for bonding, and as a result we can delocalize our electron density in our pi bond via resonance. Okay, so let's label the rest of our hybridizations. And just to make sure we're paying attention here, what about this rightmost carbon? What's the hybridization of this rightmost carbon? sp3, perfect. Okay, perfect. So we've completed this example. This is something similar to what you'd see on an exam, where you consider all the different resonance structures and you use your resonance structures to draw a conclusion about bond length and strength. This is actually observable experimentally. This is observable experimentally. If you wanted to, and if you studied and you wanted to look at each of these carbon-oxygen bonds, for example, you'd actually see a different readout if you took an infrared spectra, which gives a readout based on the bond's length and strength, among other factors. So these factors that we're able to estimate by drawing out the resonance structures are experimentally observable. And it's important to consider these factors because it can allow you to make sense of the data that you've collected. Does that make sense to everyone? Is everyone comfortable with these examples? Any questions before I let you loose on one of these examples as well? If not, well, if we're comfortable with this, I'd like you to look at the following two structures. I'd like you to tell me which structure has the strongest carbon-nitrogen bond. I'd like you to indicate the hybridization of each atom. And I'd like you to tell me which structure has the shortest carbon-carbon bond. So you're going to need to draw some resonance structures here. And I'll give you about 4 to 5 minutes on this example to answer the following questions. Now, to give you a little bit of space, I've panned down, and you're more than welcome to use the annotate tool to start trying to draw some of the resonance structures so we can discuss as a group. So now don't be shy to draw out your resonance structures, or you can share your proposed responses in the chat. And I'd be happy to provide feedback. And if you have any questions, don't be shy to ask a question, and I'd be happy to provide feedback in the chat or verbally. And really don't be shy to share your proposed resonance structures using the annotate tool. And we'll discuss this example in about another 4 minutes. Or if you have a question working through these examples, don't be shy to ask it in the chat or verbally. And just to make sure, the annotate tool, there's a little tab. It's a little black drop-down menu for zoom options, and annotate is one of the options. It would be really useful to have some drawn structures, as it provides me insight into the logic that students are using to solve their problems. If not, I at least want to see a few responses for which structure has the strongest carbon-nitrogen bond. And then we'll discuss this example momentarily. So let's keep on working with trying to draw out the resonance structures. If anyone would like to contribute a resonance structure drawing using the annotate feature, that would be perfect. If not, to allow us to have a productive discussion, what I'm going to do in about 1.5 to 2 minutes is I'll draw out the resonance structures, and then we can analyze the resonance structures that we have. And just as a reminder, there's a little black tab under Zoom meeting settings, where you can go to the drop-down menu and find the annotate tool. Is that the original structure, or is that a proposed resonance structure? Would nitrogen have a complete octet in that case? Would nitrogen follow the octet rule?
That's a good point. No.
Your idea is on the right track. The arrow pushing just needs to go in the other direction.
Like making it a lone pair on the carbon?
Yep, exactly. Exactly. Yeah, that could work, but it would be a minor structure. So let's do a review of resonance structures, and let's work through drawing these resonance structures together, just to give everyone a little bit more clarity. So let's look at this first structure on the left. And the pieces are starting to come together. So we're starting to see some positive improvements. The structures that I'm seeing this session are certainly much better than the first session set of structures. So when I think about resonance structures, I always like to think, where is my electron density? Where is my lone pair? And what pi bonds can I delocalize my lone pair to? So I have my lone pair adjacent to a double bond or a pi bond. So I can kick my lone pair down, and that breaks my pi bond, and that generates a lone pair. This is the very classic arrow pushing method that you're going to be using a lot when you're drawing your resonance structures. So that in turn gives us the following resonance structure. Notice we move our electron density from our region that's electron rich, from our lone pair, and we delocalize it through our pi system or pi bond. Likewise, we now, starting from our lone pair, we can kick our electron density across our pi system and generate the following resonance structure. Remember, we can only delocalize our electron density across atoms that are participating in resonance, atoms that contain a pi bond, an empty p orbital, or a lone pair in a p orbital, or in other words, a lone pair adjacent to a pi bond. So this in turn gives us the following set of resonance structures. Does this make sense to everyone? Does this arrow pushing logic make sense? So you start from your source of electron density and you delocalize your electron density through your pi system. You want to make sure you're following the octet rule, and you can only draw resonance structures. You can only delocalize your electron density across pi systems. And if it makes it easier to keep track of, you can draw out your hydrogens just to make sure you aren't breaking the octet rule. So for example, in the bottom structure, I'll draw out my hydrogens here just to make it explicit what I can and can't do. So I can't really delocalize my lone pair like this, because there's no pi bond or there's no pi system on this adjacent carbon. This carbon is sp3. I can, however, kick my electron density down into my pi system and break my pi bond. And that in turn would give me the following resonance structure. Does that make sense to everyone? So make sure to draw out your hydrogens. If you're ever stuck, whoops, I forgot a carbon here. There we go. So make sure to draw out your hydrogens. You can only delocalize electron density via resonance across pi systems and pi bonds. So now that we have our two structures, I'd like you to take a moment, and I'd like you to try to calculate the carbon-nitrogen bond order. And let's pick just the bottom carbon-nitrogen bond. It's arbitrary, but it's representative in each of these structures. So let's take about a minute and a half and let's try to calculate the carbon-nitrogen bond order in each of these two structures. And we'll discuss this example in about another minute and a half. And we'll discuss this example in another minute. It's good that I see responses in the chat for the bond order calculation. And we'll discuss momentarily. If anyone has another different response for the bond order calculations, I'd be happy to consider them, and they would really add to our class discussion as a whole. And if you have any questions, don't be shy to ask it in the chat. So for the carbon-nitrogen bond order in this top structure, in our first structure, we have a bond order of 1. Second structure, a bond order of 1. Third structure, a bond order of 2. We have 3 total structures, and that gives us a bond order of 4/3. So another estimation method that you can use, you can take the number of pi electrons and you can divide it by the number of atoms. And that gives you an estimate for the relative amount of electron density distributed in each of our bonds. So in this case, we'd have 6 electrons distributed over 5 atoms. I personally prefer the bond order method, but both of these methods can convey and give you a sense of the relative bond strength and the relative amount of electron density in each bond. So in our bottom example for our carbon-nitrogen bond order, we have a bond order of 1 in our first example, a bond order of 2 in our second example. We have 2 resonance structures, and that gives us a bond order of 3/2. So this bottom structure would have the stronger carbon-nitrogen bond. Does that make sense to everyone? Does this make sense so far? So then what we're going to do is we're going to look at the carbon-carbon bond strength. So we're going to look at our carbon-carbon bond strength. And I'd like you to take a moment and try to calculate the carbon-carbon bond order in each of our structures. And then from this information, I'd like you to estimate which of these structures has the strongest carbon-carbon bond. You're looking at both of the carbon-carbon bonds, but if you want to do a one-to-one comparison, you can look at this carbon-carbon bond here, as that would be representative. Yep, that would be perfectly representative, but it would be important to look at all of the carbon-carbon bonds in your structure just to make sure there aren't any stronger carbon-carbon bonds in your molecule. So I see some pretty good carbon-carbon bond order calculations. So let's discuss this example. So first and foremost, if we look at the bottom carbon-carbon bond, we have a bond order of 2 plus 2 plus 1 divided by 3 total structures. That gives us a bond order for our bottom carbon-carbon bond of 5/3. Okay. For our bottom structure, we have a bond order of 2, a bond order of 1, divided by 2, and that gives us an average bond order of 3/2. So we would expect, just via estimation, that the top structure would have a stronger carbon-carbon bond. Now, of course, the first neutral structure is predominant in each of these resonance structures. So the actual difference in bond order between these two structures is not going to be extremely large. But nonetheless, one thing that you do want to keep in mind, in each of these resonance structures, as we notice, because we have more of our electron density shared as a carbon-nitrogen bond in this bottom structure, less of our electron density relatively is shared as part of our carbon-carbon bond. So we have a stronger carbon-nitrogen bond in our bottom structure at the expense of our carbon-carbon bond strength. Does that make sense to everyone? We only have so much electron density to go around. So that in turn affects the relative strength of each of our bonds that have electron density delocalized via resonance. This is an estimation method, but I find it's really valuable as it helps you put some numbers to these soft ideas of, well, this bond is stronger, well, this bond is weaker. Does this example make sense to everyone now that we've gone through it together?
Yeah, quick question about just resonant structure drawing in general.
Yes.
When we form a new double bond with nitrogen's lone pair, we
Yep.
have to break that
Yes.
double bond on the bottom, otherwise it would change its geometry and thus not be constitutional.
So otherwise, it would not follow the octet rule.
Oh, right, because it's carbon. Oh,
Yes.
that's right.
Yes. And the best way to visualize that is to draw out the hydrogens, and then from that, we can, if we have a lone pair and a double bond, then this carbon would break the octet rule. Likewise, if we formed a double bond and we had 2 double bonds and a hydrogen, this carbon right here would have 5 bonds. So do you see?
Yeah, I see it.
Okay, perfect.
Yeah, I always forget about the inferred hydrogens.
Yeah, and that's partially why, especially early on when you're drawing resonance structures, try to draw out the implied hydrogens, as that can often make many common errors when drawing resonance structures very, very apparent and obvious. I know sometimes the book doesn't draw a lot of the implied hydrogens, and in later parts of the class we'll just always be aware that these implied hydrogens exist, but especially early on, just drawing out any of our implied hydrogens will help us see whether or not we're still following the octet rule. Does that make sense?
Yeah.
Perfect. Are there any other questions I can address on this example? If not, let's talk a little bit about resonance hybrids. So the weighted average of all resonance structures is known as the resonance hybrid. So we've already started to draw resonance hybrids, and the main use of a resonance hybrid is to identify and describe the distribution of electron density in our molecule. The distribution of electron density in our molecule as the result of resonance effects can be determined by looking at the partial charge of each atom in all major contributing resonance structures. So for example, in this first structure here, we can draw a resonance structure by kicking our lone pair down and in turn moving our lone pair onto the carbon. That in turn would generate the following resonance structure. This is known as an enolate resonance structure.
What makes it an enolate?
So an enolate is a general functionality where we have a carbon anion adjacent to a carbonyl functionality. This motif is known as an enolate. You'll see a lot of these structures in organic chemistry too. I always like to put names to common structural motifs that you'll see later on. And this is the common name used for this carbon anion adjacent to a carbonyl. So, as we notice, we have a negative charge on oxygen on our first resonance structure and a negative charge on carbon in our second resonance structure. So if we were to draw a resonance hybrid, we would say in our resonance hybrid, we have a negative charge distributed across our pi system. We can be a little bit more explicit here in that in our resonance hybrid, which two atoms have a partial negative charge? Which two atoms have a large amount of electron density in each of our resonance structures? Which of our atoms have a lot of electron density? Which of our atoms do we draw a negative charge in each of our resonance structures? Oxygen and carbon. So we can denote that with a delta minus. So delta minus indicates regions that are electron rich. So this carbon is electron rich. There's a lot of electron density distributed on that carbon. And by identifying sites that have a lot of electron density and sites that are deficient in electron density, we can begin to rationalize reactivity. So for those who are potentially curious, what locations could an enolate be particularly reactive at? Which atoms are particularly potentially reactive? Which atoms have either excess electron density or are deficient? The oxygen and carbon, exactly right. And that's why enolates can react at oxygen or carbon. See, immediate connection between the distribution of electron density in our resonance structures and our resonance hybrid and reactivity principles that we'll see later on. Okay, so looking at this next structure, we can draw a resonance structure by kicking our double bond to form a new double bond with our carbon, which has an empty p orbital. I'm just drawing this out just to show this carbon is sp2 hybridized, it has an empty p orbital. We can form a double bond. That in turn gives us the I drew the same structure again. That in turn gives us the following resonance structure. And as a result, our resonance hybrid would look something like this, where we have our positive charge distributed across multiple atoms. We can be more explicit here. in these structures, which atoms have we drawn a localized charge? Which atoms have a partial positive charge in this bottom molecule? Do all of the carbons have this very localized charge in their resonance structure? So looking at each of our resonance structures, which two carbons, the left and right carbons, exactly right. These carbons are especially electron deficient, and these sites are potential sites of reactivity. Does this idea make sense to everyone so far? We draw our resonance structures. Wherever we see localized charges, those in our resonance hybrid, we indicate with partial charges as potential sites that are electron rich or electron deficient. Does this idea make sense to everyone? Any questions? Okay, so to describe regions with an excess of electron density, we use a partial negative formal charge. To describe regions with a deficiency of electron density, we use a partial positive formal charge. When formal charges are delocalized on multiple atoms, the charge at a given atom in the pi system is a partial formal charge. So we've already seen this before when we looked at something like acetate. We can draw a series of resonance structures for acetate. And in turn, our hybrid would look something like this, where we have our partial negative charge on both of our oxygens. It's not a full localized charge because that negative charge is distributed across multiple atoms via resonance. Does this make sense to everyone so far? Any questions so far? Perfect. So let's do an example. So I have a series of examples proposed. And what we're going to do is I'm going to do the first one and you'll do the second one. So let's look at this motif that we've seen time and time again. Now, this structure is known as an enamine, and you'll see this motif a ton in organic chemistry too. It's a relative of the enolate, in fact. This actually probably also gives you a hint into how this structure behaves, and we'll see why this structure is a relative of the enolate. So first and foremost, what we're going to do is we're going to draw out some resonance structures. So first, I'm going to kick my alone pair down, and I'm going to break my double bond. That in turn gives me a resonance structure that looks something like this. Okay, another possible resonance structure that we can draw, though this one's pretty minor. That's why I'm drawing this in a different color. This is a minor structure. Now, when we talk about minor structures, they're not necessarily bad. These minor structures give us a lot of information into potential patterns of reactivity, and it can help us notice potential atoms that are electron deficient, but that aren't found in major resonance structures. So we've drawn out each of our resonance structures now. So let's just do a little bit of a map now and identify in each of our resonance structures which atoms have a negative formal charge, which atoms are electron rich. Which atoms are electron rich? Which atoms contain lone pairs or contain a partial negative charge? Yep, so this bottom right carbon is electron rich because we have a minor structure and another somewhat major structure with a negative charge on this bottom right carbon. The nitrogen is electron rich because there are many structures where the nitrogen has a localized lone pair. What about this middle carbon? What about this middle carbon? What about this middle carbon? Is this middle carbon electron rich or electron deficient? Looking at our major and minor structures, is this middle carbon electron rich or deficient? Well, we see a positive formal charge here. So this middle carbon is somewhat electron deficient. So we've already started to generate a map of the relative amount of electron density on each of our atoms based on resonance effects. Pretty cool, right? Does this make sense so far? So what I want everyone to do now is I want everyone to take a moment and to try and draw resonance structures for the following molecule. And I'm going to start you off with one of the resonance structures just to keep things a little bit more constrained. So the first resonance structure that you can draw that you're going to build off of is the following, where we kick our double bond up to form a lone pair. That gives us the following first resonance structure, and I'd like you to build on and draw the remaining relatively major resonance structures for the following molecule. And we'll discuss this example in about 3 to 4 minutes. And I'd like to see a few students contributing their structures using the annotate tool. Yep, the arrow pushing looks good. And make sure to include your formal charges as well. And would another classmate like to provide another additional structure for us to consider? So this first structure looks good. Let's put the formal charges into this first structure. And then would someone else like to provide a second resonance structure for us to look at? We still need the formal charges on this first resonance structure, and then we need one more resonance structure to complete our analysis of this molecule. So you're very close. You're very close here. Let's actually talk about this example now. Let's talk about this example because we're on the right track. We're almost there. So first, the first structure that your classmate indicated was with this arrow here. That's a perfectly fine arrow pushing depiction to get to this next resonance structure, which looks something like this. Now that we have the following resonance structures, if we draw out our hydrogens, let's make all of our hydrogens explicit. And if we look at this carbon right here, if it has 3 bonds and that's it, what would the formal charge be on this carbon? Positive, yep. Now what we're going to do is we're going to kick our double bond up and we get the following resonance structure. Now if we have 3 bonds on this bottom carbon and that's it, what is the formal charge on this carbon? Positive. Okay. So then, in our analysis, which carbons have a positive formal charge? So let's start up here. So this first carbon, is this carbon electron rich or electron deficient? Is this first carbon electron rich or electron deficient? The carbon that I've marked in red. This one right here. Is this carbon electron rich or electron deficient? Do we see a positive charge or a negative charge? It's deficient, so we draw this with delta plus. Okay. What about this next carbon? Which matches this one right here. Is that carbon also electron deficient? Does it have a positive charge in one or more of our resonance structures?
Yes.
Yes, so we write it with delta plus. Finally, our last carbon here, is it electron rich or electron deficient?
Deficient.
Yep, exactly right. Now, we can actually draw another set of resonance structures, and I'll show them right here. If we take this resonance structure and we manipulate it further, we can notice that we have a few atoms that are pretty electron rich. So first, we kick our lone pair down and we break our double bond. That in turn gives us the following structure. Next, we can kick our lone pair down and break our double bond once again. And that in turn generates another resonance structure. That looks something like this. So, continuing on with our trend, we notice that this first atom that I've marked in blue, is that carbon electron rich or electron deficient? Is the carbon that I've marked in blue, also known as an alpha carbon, is that carbon electron rich or electron deficient?
Deficient.
So what charge do we have on this blue carbon, which is right here?
Oh, sorry. I meant to say rich, but
Oh, that's
sorry.
okay. That's okay. Exactly right. It's electron rich because we have a negative charge in one of our resonance structures. What about on the gamma carbon? Is that gamma carbon electron rich or deficient? Do we have a positive or negative charge? It's electron rich because, as we can see on this gamma carbon, we have a negative charge in one or more of our resonance structures. So as we can notice, is there any electron rich atom that we're missing here? Any electron rich atom that we're missing? Oxygen, yep. Oxygen has a negative formal charge in a lot of our resonance structures. So by drawing out all of the resonance structures, noting which atoms have a negative and positive charge, we can denote and we can indicate the electron rich and the electron deficient atoms. This is why when you look at these unsaturated ketones, they typically react at the central carbon, the beta carbon, or so in general, addition either occurs at the in general, addition will either occur at the carbonyl carbon, the beta carbon, or this other conjugated position, because we have 3 sites that are electron deficient. So if we attack it with an electron rich atom, that electron rich atom will attack at one of these 3 electron deficient sites. You don't have to worry about this immediately, but this can help you understand patterns of reactivity if you can identify the atoms that are electron rich and electron deficient. Does that make sense to everyone? Is everyone starting to see the connection between sites of electron density and electron deficiency, and how that can connect to patterns of reactivity that we observe for different chemical reactions? Does this example make sense? Perfect, perfect. So what we're going to